This is Knight section 2.3, finding position from velocity. Let's just flip back to 2.2 for a moment. In 2.2, we found velocity from position. And the way we did that was we took a graph of position as a function of time. Notice this is not a motion graph. This is position as a function of time. So this might represent somebody who was going slow and speeding up and then maybe coasted for a little bit and then started slowing down again. We imagine looking at a very small zone of that graph, let's say like that, and we imagine pressing our face up against that zone, and if you look really closely, I'm going to blow it up here, well, maybe you can still see the fact that it curves a little bit as it goes through that zone, in which case make an even smaller box. Okay? Now, in this tiny box, it looks like it's going through here straight. So there's the tiny box. This is a blow up of this portion of that large graph. In this region, since we've gotten so close we can no longer see any curvature, essentially we're going at constant velocity in that region. And what is the constant velocity? Well, if you can take, once you've got a straight line, you can take any height over any distance. I could take that height over that distance, or I could take that height over that distance. It doesn't matter if it's a straight line. You can take as short or as long a rise over run as you like, and you get the slope by calculating the rise over the run. And the rise over the run is the distance traveled, that's the change in x, and the run is the change in t, so the rise over the run is the change in x over the change in t, which is precisely what we mean by the velocity. So now, with that little review, we have to go the other way. Suppose somebody gave us the velocity graph for this. Okay, so I said this corresponds to somebody picking up some speed and then coasting a bit. So here they're picking up some speed, and then they're going to maybe coast for a bit, which means they're going to go at constant speed, and then maybe they're decreasing in speed. This is now velocity as a function of time. How could we go from this to the position? Well, what you do is this. Once again, you have to kind of adapt to the idea that things are changing by looking at a very small region where they're not changing much. So let's just focus on a little region right here. Okay? I'm going to just focus on a little region right here on this graph, okay? And this is going to have width delta t. Now, as you can see, the particle was going a little faster at this point than it was going at this point. But if we make this zone pretty narrow, then, and I'm going to narrow it up a bit, if we make this zone pretty narrow, you see that the difference in speed at the final point versus the beginning point in this new narrower region is starting to get smaller. And maybe I can make a really narrow region where you can hardly tell the fact that the velocity has changed over that region. I'll make a nice narrow region. So, okay, now the velocity was this much at the before the delta t and this much after the delta t. And as you can see, it hasn't changed much. So maybe there's not much error in just using, say, this v at t as our estimate of the velocity. Of course, you could use this v at t plus delta t as your estimate of the velocity, but the whole reason we took a very narrow slice is because v at t and v at t plus delta t are very close to each other if this time delta t is very small. Now, what is the distance traveled in that time? Well, if we can say that it's v of t, the person was going at v of t, or v at t plus delta t, doesn't matter much which. If we say the person was going v at t For a time delta t, well, from the old distance equals velocity times time problem, it looks to me like this person went v at t times delta t. That's how far they went. Now the interesting thing about that is that has the interpretation of being this width times this height. In other words, that has the interpretation of being that area. The area of that little rectangle, its height v of t and width delta t. And we can repeat this. We can say, well, the person went v at t times delta t distance. What did they do in the next amount of time delta t? Oh, well, again, I'm going to approximate this little thing, this by taking the left edge here. And I have another width delta t. And how far did the person go in this? Well, the left edge, they were going v of t plus delta t. They did that for another delta t of duration. So that's their additional distance traveled, which has the interpretation of being that. Now, you just keep on going like this, breaking this thing up into chunks of delta t in width. So now I've sliced this thing into ribbons all the way from the beginning to the end. And we can ask ourselves, how far did this person go in this time? Well, they went this speed right here for delta t, then they went this speed for delta t, and they went this speed for delta t, and this speed for delta t, and this speed for delta t, etc., all the way till they went this speed for delta t. Interesting. What we've shaded here is actually a whole bunch of widths times heights whose total width times height is the area under the curve. That's what mathematicians call the integral, but here let me write it. What it is it's the sum over all these terms. That is, it's a sum from the 0th place, say, to the n minus 1st place. So we've broken this thing up into n chunks. It's the sum from I equals 0 to n minus 1 of v at I times delta t times delta t. Or you could write it as sum I equals 0 to n minus 1 of v at t sub I times delta t. I'm kind of assuming here that all the delta t's have the same width. You don't have to assume that. You could make these delta t sub i's as long as you make them sufficiently narrow that the little error that you've made right here, you see these little errors? See right here I used v at t, I used the little left edge. If I'd used the speed at the right side, I would have had that area instead of that area. As long as these are sufficiently narrow that that error that I made, which is that little area right there, that's the most I could estimate versus the least I could estimate, is that difference right there. As long as they're sufficiently narrow that that difference is negligible, then this is the total distance traveled. Okay, now when you say something like, as long as these widths are sufficiently narrow, what you really mean is limit that delta t goes to 0. Now, if all the little widths are going to 0, that means all the number of slits is going to infinity. So the limit that delta t goes to 0, while capital N, the number that I broke this up into, is going to infinity, the limit that delta t goes to 0, n goes to infinity, of this sum is the distance traveled and is the area under the curve. So, bottom line, we have to learn through practice, which we'll do in class, we have to learn how to apply a rule like this